Welcome. This is now video number 12 on the exploration of hyperreal numbers. Today we are going to talk about the transfer principle. We are not going to prove the transfer principle, but we are going to discuss various examples and constructions which should help you understand it. In simple words, the transfer principle allows you to push a mathematical statement from R to star R and inversely. However, those mathematical statements are submitted to constraints in the way we express them. It is therefore important we agree on the mathematical language. So let me first define a relational structure as a triplet built on a non-empty set S, a collection of finitary relations, and a collection of finitary functions. In particular, we talk of a full structure when both collections include all possible finitary relations and functions. We are writing curly R, the full structure built on the real numbers, and star curly R is this object here, the triplet built on the hyperreal numbers with a collection of all extended relations and all extended functions. Importantly, you can convince yourself that this structure is not a full structure. We will come back to that a little bit later. Let me here talk about the terms of a given language, or LS terms. Any string of symbols representing variables, constants, and functions are terms of a language. For example, x plus 2, x over y, sinus xy plus pi are all terms of the LR language. In particular, a term is said to be closed when it includes no variables. We define an atomic formula of the language as a k-ary relation of k terms. For example, x larger than 5 plus 2 pi or pi equals sinus y plus 2 are atomic formulae. Another example is x belongs to P, where P is a subset of S, which is here a unary relation, and therefore it's an atomic formula. To build formulae out of atomic formulae, we need the following logical symbols: and, or, not, implies, if and only if, for all, and they exist. From atomic formulae, we can build a bigger formula simply called a LS formula. Any atomic formula is also a LS formula. The logical connection between two formulae is a formula, and so is the negation of a formula. And if x is a variable and p is a unary relation, then those two statements here are also formulae. Here we have an example of a formula made of two atomic sentences, each made of two terms, including variables and constants. A variable is a formula, a variable in a formula is either free or bounded. In the first example, the variable is free. In the next one, it is bounded by the set x, but you see the variable y is still free. A statement with a free variable is neither true or false. You see that this statement here cannot set to be true or false until you know what are the possible values allowed for x. Finally, we define a sentence as a formula with all variables bounded. And so to summarize all that, we have constants, variable, and functions, which are all terms of a language. Relations between terms are called atomic formulae, and the logical connections between atomic formulae gives us formulae. And any formula with no free variable is a sentence. So I can now tell you about the transfer principle, which is stating that a defined LR sentence, call it phi, is true if and only if the sentence star phi is true. The question left here is how do we transform a sentence phi to the language of the hyperreal? There are rules which we need to follow, and we pretty much have to add a star everywhere, on relations, on terms, on formulae, on sets as well. So that by following those rules, you can in principle push any sentence on R to the hyperreal numbers. As always, as we become more comfortable with the star notation, we tend to drop it. So here is a formula with the transform in the language of the hyperreal numbers. And you see there is a lot of star symbol which we do not really need. Hence we are dropping most of them, but keeping it when it is important on the sets. We tend to also keep the star notation on a non-familiar k-array relation. A mathematical statement needs to be appropriately formulated if you want to apply the transfer principle on it. So you need to be able to write a LR sentence. That's basically what appropriately formulated means. Then it is transferable, meaning that you can apply the transfer principle. Let us take an example with this sentence. For all x in R, x is not equal to 0 implies there is a y in R such that x times y is equal to 1. Which simply becomes, under the transfer principle, for all x in star R, with x different from 0 implies there is y in star R such that xy equal to 1. Which is telling us that what we already knew is that there is an inverse for all non-zero hyperreal number. We can also apply the transfer principle on a sentence such as this one, which simply becomes the following, and which is very reassuring because it is telling me that I can manipulate exponential of hyperreal numbers in the same way I would manipulate the exponential of real numbers. This is in fact an example of what is called universal transfer. If a property holds true for the real number, then it holds for all hyperreal numbers. A little more confusing is the existential transfer, stating that if there exists a hyperreal satisfying a certain property, then there exists a real number with the same property. My first reaction, of course, is to think of this statement here. There is a n in star R such that for all x in R, n is greater than x. If this statement is true, it is obviously not transferable back to the real numbers. So somehow this is not an appropriately formulated mathematical statement, and let us see why not. Let us go back to the transfer principle, where phi is true if and only if star phi is true, where phi is a LR sentence constructed on the full structure R. I could also say that a L star R sentence, star phi, is true if and only if phi is true. Or if you want, I could call star phi psi, and I could replace phi by lower star psi. But if you get confused about this, don't worry about it. What is important here is that star phi is constructed on star R, which is not a full structure. Let us look at star R once again, and the sentence here. This section expresses a unary relation, since R is a subset of star R. However, we see here that all relation needs to emerge from the extension of a relation on R. The problem is that the set of real number cannot emerge as the extension of any unary relation. Basically, think of star R as a toolbox we are given to build sentences on the hyperreal number. When writing this sentence, here we are using tools which are outside the toolbox we have been given, and which is why the statement is not transferable, and therefore the existential transfer does not apply here. One more theorem I would like to mention is Low's theorem, stating that for any LR formula, the L star R formula, which is here, is true if and only if the statement here is true almost everywhere. You can think of it as a generalization of the way we had defined the equality. We will see an example with the next slide. So this brings me to a hyper formula. Here I'm trying to repeat the same old trick, creating an infinite sequence of objects to create an hyper object. Let us, for example, look at the statement which is here. X relates to tau, where x is a variable and tau is a constant. For x equal a1, phi is either true or false. So I build the sequence phi a1, phi a2, and so on. I have a sequence which is either almost true everywhere or almost false everywhere. I'm calling this equivalence class star phi of the hyperreal A, which is defined by the sequence of the an values. This statement is true if and only if the statement here is true almost everywhere. What we have here is indeed an example of Low's theorem. Let me now replace the variable by a constant, for example 2. The statement now is either true or false. The extension of this statement is given by the equivalence class of the constant sequence, which is therefore taking the truth value of phi 2. So whatever is the truth value of this statement, the extension must take the same truth value. Let us now move on to another statement, phi, which we assume to be true. For all x in the set x, x relates to tau, where tau is a constant. Let me now define star phi as the equivalence class of the constant sequence phi, which obviously is true. The question which is now left is, can I be sure that this object star phi indeed identify to the sentence which is here? So let me one more time write star phi, where each element is the sentence in the sequence is the statement phi itself. For a finite set x, I can rewrite the statement using the logical AND and running all over possible x values. Now let me build this object here, the equivalence class of the sequence for some xn I have selected in the set x. Since x relates to tau for all xn, each element of the sequence is true, and therefore the statement here is true. In fact, we can write this statement as curly x relates to tau, where curly x is a hyperreal number built on the sequence of xn value. This statement, being true for all possible curly x I can possibly construct, I can now write for all curly x in the set star x, curly x relates to tau. And obviously, we do not need to keep on writing the variable curly x. Using a simple x would work as well, which leads us to the transferred statement. Okay, that is the end of this video. Thank you for your time.